The next topic that we want to talk about is work. This is going to be the first of three discussions where we talk about different aspects of this topic. The first one is going to be about Hooke's Law. Before we talk about that, we need to remember what we've called work in the past. If I have an object and I exert a force on the object F, causing the object to move a distance d, then work was defined to be force multiplied by the distance. For example, if I have some rectangular object and I move it 10 feet by applying a force of 20 pounds, the amount of work done is force times distance, 20 times 10, 200 foot-pounds if we're using imperial units of measurement. This assumes three things. The motion is in a straight line, the force is in the same direction, is parallel to the direction of motion, and the force is constant. I started off pulling on the object with 20 pounds of force, and I continued doing that until I got it to where I wanted it. There's a technical point we need to be aware of. In ordinary English, when you say that you're doing work, that makes an image in your mind of exerting effort or doing something of this nature. In the technical definition of work, it's a little bit different. If you have this individual named Fred, represented by this atrocious stick figure, and Fred is pushing against a brick wall with a force of 20 pounds, Fred is exerting effort, but technically speaking, since the wall doesn't move, Fred isn't doing any work in our sense of the word because the distance the wall moves is zero. Likewise, if you have a spring and someone, we'll call him Fred again, pulls the spring out a certain distance from the wall, and then after that just holds it in place, even though he can feel the spring pulling on his arm, he isn't doing any work after that initial displacement because it's not moving any. He isn't exerting any work in keeping the thing stretched, which is going to be a key feature of calculating work using Hooke's law. There is an unlimited number of work problems that you could think about. We're only going to look at three. The first one, Hooke's law, has to do with springs, which we'll talk about in this discussion. In the next one, we'll talk about Newton's law of universal gravitation. And in the last one, we'll talk about the work done by an expanding gas in a cylinder. Our first case is Hooke's law. A spring has some natural length or equilibrium length, which is the length of the spring with no extra forces acting on it. You could think of having such a spring and attaching a weight to it so that the spring is stretched downwards. We're going to call that the amount that the spring is stretched away from its natural length, x. And we need some sort of formula that relates the force involved to the amount of displacement that you get. Hooke's law says that the relationship between the amount of displacement and force is actually a very simple one. It's linear. For a given spring, there's a constant k to go with it, so that the force needed to stretch the spring by a displacement of x is just force equals k times x, where k is often called the spring constant for obvious reasons. If someone tells you that it takes 10 pounds of force to stretch a spring by 12 inches, then force equals k times x. The force is 10 and the displacement is 12 inches. So if I want to use pounds and inches for my units, then the K would be 10 over 12, which is 5/6. The force is then given by 5/6 times x. Now, if I wanted to use feet for my units of distance, 12 inches is a foot. So if I were using feet, 10 would be K times 1 foot. The K would be 10, and the force would be 10 times x then. So the exact value of this constant depends on what units you're using. Suppose you had a spring and its force displacement relationship was force equals 10 times x. If x were 2, the amount of force associated with displacing the spring to 2 units is going to be 10 times 2, which is 20, and we'll assume we're doing foot-pounds. If you stretch it out to 6, the force involved is 10 times 6, which is 60 foot-pounds. If x is small, the force is small, and if x is big, the force is big. So this is not a constant force. Our idea about work equal force times distance doesn't apply here. It won't work. If you do that, you'll get the wrong answer. Think of having the natural length of a spring. I'll call that x equals 0. X is the displacement from natural length. And then we're going to stretch the thing until it has some displacement d from the displacement, d from the natural position. X equals 0, no displacement. X equals d, the full displacement that we're after. We want to calculate the amount of work that's needed to do this in some format or the other. And I already know that multiplying force times distance is not going to do it for me. So you can imagine what we're going to do. We're going to chop the region from x equals 0 to x equal capital D up into a number of smaller subdivisions. We're going to figure out the amount of work needed on each subdivision, at least approximately. Then we'll add up all those contributions and we'll let the size of the little subdivisions tend to 0, and hopefully we will get something that we know how to calculate. Now, to be specific, I'm going to think of having 4 subintervals. In the first subinterval, the x value goes from x0, which is 0 in this case, to x1, whatever that is. I'll call the width of that interval delta x number 1. The force is going to be represented by f of c1, where c1 is some x number in that first subinterval. So the force on interval number 1 times the distance for interval number 1 is going to give me approximately the work done on subinterval number 1. Now you can imagine Fred stretching the spring from x equals 0 to x equals x1 and then holding it. The amount of work that Fred's done is this f of c1 times delta x1. For Fred to hold the spring at that displacement costs no more work, as we've just seen a moment ago. So then I'm going to start at x equals x1 and stretch to x equal x2. That's the second of my subintervals. Pick a representative x number in the second subinterval between x1 and x2. The amount of work done on the second subinterval is approximately f evaluated at c2 times delta x number 2. where C2 is some number in subinterval number 2, then play the same game on the third and fourth subintervals. The total work is then given by the amount of work on each subintervals from 1 to 4 summed up. It is equal to that quantity. If you've been following along, you already know what's going to happen. If I had n subintervals instead of just 4, I would have n such contributions. The work would approximately be the sum I equal 1 to n of f evaluated at ci times delta xi. And to make the exact value come out, I need to take the limit as all of the delta xi's tend to 0. And there, once again, is a Riemann sum. Take the limit of it. It turns into an integral. The smallest x value in this scenario is at x equals 0. The biggest displacement is being called d. I have a formula for the force, and I'm going to integrate that with respect to displacement, and this is going to tell me how much work I've done. In fact, if I have some force that depends on a variable x, the force points along the same direction as the displacement. I have some initial value of displacement, which for us right now is 0, and some ending one. This is generic. This applies not only to springs, but to any force acting on an object that moves along a straight line, assuming that the force is in the direction of the motion. The force doesn't have to be a constant. It doesn't even actually have to be the spring force. For example, for a certain spring, the force needed to cause displacement x is F equals 16 times x. Our spring constant k is 16 in this case. If you start at x equals 0, at the natural or equilibrium length of the spring, you're going to stretch the spring until it's 5 units from its equilibrium. How much work is done in doing that? Based on what we said already, this is almost an insult to your intelligence. We are supposed to integrate the force as a function of x from the starting x value to the ending x value, and this turns out to be perfectly straightforward to do. The answer comes up to be 200 foot-pounds, or if you were using metric units, joules, or if you're using air conditioning units, British thermal units, or whatever your units happen to be, that's not going to be a big issue for us. You don't have to start at the natural length, though. You might imagine somebody named Fred stretching the spring until it's been displaced A units from equilibrium. So Fred did this work. Fred then holds the end of the spring still, and even though he feels it pulling on him, he's not doing any more work. His friend Jim comes along and takes over from Fred. Jim grabs the end of the spring and holds it still, not doing any work yet. Fred lets go, and then Jim stretches the spring some more until its distance from equilibrium is B. How much work did Jim do? Jim wasn't involved in the early on business. Fred was doing that. So Fred did the part of the stretching from x equals 0 to x equal a. Jim did the work from x equal a to x equal b. If you go back through the logic of what we said before, it's exactly the same, except the starting x value is a instead of being 0. And that leads to the conclusion that the work that Jim did is the integral from a to b of force of x dx. And once again, this is generic for many types of problems, not just the spring problem. For example, a spring has Hooke's law F equal 20 times x. The K is x here. We'll measure our forces in pounds and our distances in feet. This is going to be stretched 5 feet, and then Jim stretches it until x equals 10. How much work was done? Having seen what we've done already, obviously, I'm going to integrate from the initial displacement 5 to the final displacement 10, f of x, the force with respect to x. This is integral from 5 to 10 of 20x dx. Evaluating that is straightforward. You get 750 foot-pounds of force. Now, keep this question in mind because I want to compare and contrast it to the next question. Sometimes people play word games. Listen to this problem. A spring obeys F equals 20x. That's the same formula as on the previous page. Initially, it is stretched 5 feet, and then Jim stretches it an extra 10 feet. How much work did Jim do? If you're not paying attention, this sounds almost exactly like the previous problem, but it's not exactly the same thing. Jim isn't going to stretch the spring until x equals 10. Jim's going to start at x equal 5 and then stretch it an extra 10 feet, which means he's going to end at 15 for the displacement instead of 10. Other than that, the calculation is exactly the same, and it turns out that you need 2,000 foot-pounds of energy or work to do this. So you need to pay very careful attention sometimes to people when they ask these sorts of questions because they'll play word games with you. More word games. Suppose that a force of 50 pounds is needed to stretch a spring 2 feet. How much work is done doing that? Here's a commonly seen wrong way of doing this. Work equals force times distance. Force is 50, distance is 2. 50 times 2 is 100 foot-pounds. This is wrong because in the force law for springs, F equals K times X. Early on, when X is very small, the force is very small. But later, when X is big, the force will be big. And this force times distance thing only works if the force is a constant. So this is a common mistake that people will make. This is totally wrong. What are you supposed to do with these numbers? The right way to deal with this situation, the relationship between the displacement from equilibrium and the force, according to Hooke's law, is force equals K times X. And what the setup of the problem has told me is they've told me what the force is for one particular X value. So if it takes 50 pounds of force, F equals 50, to achieve a displacement X of 2, then it must be true that 50 equals K times 2. That lets me figure out that the K is 25. So now I know what the force law is. That's why I needed that backed up front concerning the force being 50 when X equals 2. Starting at X equals 0 and ending at X equals 2, the work involved is the integral from the starting X value to the ending X value of the force with respect to X. And the force here is force equals 25 times x. Antiderivative, 25 over 2x squared. Evaluate between x equals 0 and x equals 2, and you find out that the force acting on the object, displacing it from x equals 0 to x equals 2, works out to be 50 foot-pounds, not the other number that you got doing it the wrong way. So we need to be very careful when we read problems to make sure we're doing what we think we're doing. This completes the discussion that I wanted to have concerning Hooke's law and springs. In the next discussion, we'll talk about Newton's universal law of gravitation. And in the third one, we'll look at the work done by an expanding gas.